Welcome to this workshop on meta-analysis. In the first part, we're going to have a look at the main theory behind it and definitions, and then I'm going to show you an example on Excel using the meta-Excel software, and then I hope we will have time to just try, let you have some time to try it out yourself on other data. Well, where is meta-analysis sitting? All of you in this room know very well what are systematic literature reviews, because all of you have performed at least one. Systematic literature reviews are among the best kind of evidence that one can have, especially, this slide is related to medicine. Now, modern medicine is based on evidence, so all the treatments and the decisions taken by doctors are informed by evidence. Evidence comes from different types of studies. This is the so-called pyramid of evidence, which is different kinds of studies that have different types of power and quality. If you see at the bottom of the pyramid, you have the least powerful kind of evidence, which is, for example, opinions and editorial of experts. So as much as one can be an expert, their opinion is not as powerful as a randomized control trial, which is among the studies at the top, which are the ones with more higher quality. In the middle, there are many others type of studies, but among the different kind of studies, as you may know, randomized control trials, for the way in which they are designed, so in the fact that they have you split your population into those who are going to be treated, for example, with a new drug, and those who are the controls, who are just going to get a placebo, and the fact that the allocation is randomized, and the fact that there is blinding and many other things, makes this kind of study one of the best possible. Systematic reviews are above that. Why? Because they collate different studies' results. And meta-analysis is the cherry on top. So once in all your systematic literature reviews, actually you have been performing qualitative analysis, because the kind of data that you were collecting was not permitting to have a meta-analysis. But the other side of the coin, the most powerful kind of evidence is having a systematic review with meta-analysis, because we will see that it allows for quantitative kind of data synthesis. So the idea is that across the world there are many different studies, maybe studying the same concept. For example, new drug effectiveness versus an old drug or versus a placebo. But all these trials will have some sort of limitations, like any kind of study. For example, maybe we perform a study at Warwick, it has only 50 participants. We performed one in Italy and it has 200, and so on and so forth. So ideally, in theory, the one with more participants will have more power. But then there are other confounders that can affect the quality of a study. And so the idea is to pull together studies that are homogeneous. Homogeneous means studies that have similar characteristics. For example, I'm studying this new drug for the treatment of people that has had an infarction who are between 40 and 60. So you are looking for this specific. It's a bit like the inclusion and exclusion criteria of a systematic literature review. In this case, the power of meta-analysis is that it's a statistical process by which you can pull together all these data. And the example there says you can aggregate 10 studies with each of them 50 patients, and then you will have a more powerful statistics that represents 500 participants, a single study with 500 participants. So it's a much more powerful result than having a single study with that. So this is what meta-analysis is for. This is an example taken from published literature. For example, they were looking at the effect of statin, is a kind of drug for people that has cardiovascular problems. And they were looking in their meta-analysis whether an intensive treatment of statin versus a moderate one was making having a significant difference for people on the reduction of adverse cardiovascular outcomes. And okay, you can see that, for example, here they were only looking at randomized controlled trials with people with at least 1,000 patients each. And they performed the meta-analysis using relative odds based on a fixed effect model. These concepts are explained in a few slides. And the power results is that they had their result was a pooled effect of 27,000 plus patients. So this is a much stronger statistics. And what they found, for example, is that using a more intense statin treatment decreased by 16% the odds of coronary death or myocardial infarction with a p-value that is significant and other good effects. So this is how, for example, medicine can be informed by meta-analysis. Well, let's start from the end, the forest plot. This is the end result of a meta-analysis. Maybe you have seen in some of the papers that you have been reading in your PhDs or other studies. And it's called the forest plot. In this case, it's taken from the example that was in the previous slide. So this is showing the impact of statin dose on death and myocardial infarction. What we have is the risk ratio. Again, here is this concept is explained later. Each row is one of the study that has been included in the analysis. So we have, for example, the study name, the risk ratio, which is the effect size. Effect size is what is used in meta-analysis for understanding how things are related, how, for example, a certain drug is having a certain effect compared to another. It can be of different forms, depending whether it's a discrete kind of variable or continuous, but this we will see later. In this case, we are speaking about a discrete kind of variable because this is probably the risk ratio for death or myocardial infarction. So it's a discrete number. Let's say those that, I'm inventing now the numbers, but those that got a higher statin course of treatment had only 5 infarction out of a total of 100 patients. Those that had a lower dose had 20 infarction out of 100 patients. And you use these numbers to calculate the risk ratio. We will see how. And what does it mean? It means that if the risk ratio is 1, there is basically no effect, no difference in the effect between high dose or low dose. While if you are in one side of the graph or the other, so to the left or to the right of the one line, vertical line, it means that there is favoring one or the other. In this case, you can see that all the 4 studies, which are the ones with the square and whisker, are all in the left side, which is the one favoring the high dosage. What you can see is that they have different lengths in the bar, like these whiskers. This is based on their variance. So how is their effect size? How is it spread across the mean value? Of course, normally studies with higher populations will have lower variance and so more accurate results. In this case, you can see here another concept, relative weight, which is how our meta-analysis is assigning weights to each study, because each study will have a different quality. We will see how this happens, but what you have to take home from this graph is that the bigger the square, the higher the weight given to the study. You can see here that the one with more weight is the study called ideal. You can also see in the number 37% relative weight. And not strangely, but as we were expecting, is the one with less variance. It has shorter whiskers. The diamond shape below is the pooled effect. So this is centered on the pooled effect of these 4 studies. So in this case, the result is around here, which is, I don't know, 0.85, probably the final risk ratio. And the two, how do you say, lateral points of of this diamond are the lower and upper estimates. So 95% of is the confidence interval at 95% level. So what we take from this is that because we have this shape which is entirely in one side of the graph, not crossing the no effect line, which is 1, what do you think this means? Is a statistically significant. The outcome would be different. Can you see my arrow as well? Or yeah. Okay, the outcome would be different if this diamond shape was crossing a bit this, which means that there is a certain percentage of this confidence interval by which the effect size could be on the other side. So this makes it not significant because it may be that high dose is good, but also low dose is good. If you have it only on one side, it means that you have a statistically significant result, which is not shown here, but you also get IITs, p-value. You have a very low p-value, so less than 0.000. So this is a significant result. Well, we have said all these concepts. I forgot there was this slide. 0.85, it means there was a 15% reduction in mortality. Normally, I think in the Excel tool we are going to use, it will also tell you the confidence interval values, not only the graphical way. So when you perform a meta-analysis, you have an effect size, which is a certain variable that we need to calculate. And this is calculated for each study. And then you pull them together based on a weight that is calculated by the model that you're going to apply. There are 2 main models: fixed effects, we're going to see, and random effects. The higher the precision of the study, the more weight it will be assigned to that study. Now, this is you all know this. What is the difference between a traditional review and systematic review? Meta-analysis, we said what adds to that? It adds the capacity of comparing actual numerical data to inform clinical practice, for example. This is another example. Let me just see where this is going. Okay, so in this case, we had meta-analysis on therapeutic trials for myocardial infarction. They looked at 30 years of study, 33 randomized controlled trials to assess the ability of this streptokinase to prevent death following a heart attack. Well, the same outcome, the outcome that they looked at was mortality, basically. So this is taken from the paper. These are many more studies included. What you can see here is that the most effect sizes, which you cannot see much of the square here, is very small, but are between 0.5 and 0.9, the 2 dashed lines. So you can see that more or less we are saying that most of the studies are stating the same. Sometimes it happens that some studies, for example, this one here or this one here, they're stating the opposite because they're across the line. So they're saying that the effect is opposite. It could be that, I don't know why this is happening, but don't expect that all the study will say that a drug is always reducing mortality. There will be some others that will be saying the opposite. And this is what heterogeneity in studies means. In this case, since they are all more or less aligned in the same effect size area, we have fair consistency, and you can use the fixed effect model, but there are mathematical ways in which you can also do that. So very quickly, which studies are the most significant in this plot? Name at least one. So what is the European 2? Yes, is one. Tell me another one. Which one is this one? GC. Yes. Okay. So there are a couple. All those that are not crossing the no effect line. All these ones in the box. Okay. What's the summary effect size? What is this saying? What is the take-home message? Is this one, right? I mean, in this case, it doesn't have a diamond. Normally, you have a diamond. So what can you see? Does it cross the one? So it's a significant. And is it to the left or right? Left. So I don't know how they have because it also depends how you set your study, but probably it means that there was a reduction of mortality. Okay. Well, this we said already. I think we can skip. Okay, and this is just showing you graphically where the meta-analysis sits. So you normally have the systematic literature review process that you all know, and then the meta-analysis sits after. So it's where you have extracted all the data in the extraction table, for example. You use that to calculate the statistics. Statistics means the effect size that could be relative risk, odds ratio, mean difference, and many others. You have to select the kind of model, fixed or random. And how do you do that? You do that assessing heterogeneity. You use this chi-square kind of test, and it gives you a couple of statistics that then you can interpret and decide whether to apply random or fixed effect. I've already said this, there are two kinds of outcomes. Dichotomic means discrete, dead or alive, positive, negative, with disease, without disease. Continuous is, for example, surgical time. Diuresis means how much urine is expelled. Blood pressure variation, so you can understand the difference. Depending on whether it's dichotomic or continuous, you have to use, for discrete outcomes, you can use odds ratio or relative risk. These are the main two. For continuous outcomes, you use mean difference or standardized mean difference. Starting from standardized mean difference is, well, the difference between, sorry, not standard. The normal difference is just the difference between two means. Standardized mean difference is the difference divided by the standard deviation. Normally, it's better to use the first one because it maintains, let's say, blood pressure is measured in millimeter of mercury. So your mean difference is, since it's just a difference, will be in millimeter of mercury. It will be easier to interpret. If you do a standardized mean difference, you divide by the standard deviation, so you have something that is not easy to interpret, but that you have to use in case you have studies that use different scales. The example here says if one study measures pain between 0 and 10 and the other between 0 and 100, you need to use this standardized mean difference, for example. Well, this is, and the confidence interval, these are just, there is quite a lot of equations in the next slides, but these are done by the software. You don't, this is just for you to understand how it works. Confidence interval is given by this formula, okay. And variance is given by this formula. So when you have a mean difference, the variance of the mean difference is given by this, and the standard deviation is given by this. So these are just taken from statistics. This isn't, we don't have time now, but you can play with these numbers. So if you have a study where the mean is 103 and the other is 100, with this standard deviation, and both have 50 subjects, the mean difference is 3, and the 95% confidence interval will be this one. Okay, risk ratio versus odd ratio. These are the two main ones used for discrete variables. And I'm sure that there will be an example later, so maybe I should directly go to the example. But this is the formula. Odds ratio is given by those people that got the treatment and are positive. We will see an example. Divided by those people that didn't get the treatment and are positive, all divided by those people that got the treatment and are negative, divided by those people that got only the control and are negative. While the relative risk or risk ratio is the same concept. I mean, it's just the same, two names for the same thing. You have those people that got the treatment and are positive against all people that are positive and negative, all divided by those people that are positive and not treated over all the people that are positive and negative. What should you use? Normally, risk ratio is the best one, especially when you use randomized control trials. The reason is that odds ratio, while risk ratio is more similar to a probability, by the way, it's defined. Odds ratio is less straightforward to interpret and tends to overestimate risk ratio. So the best you can do is to use relative risk. Now, well, let's do this example. So in this case is fictional data, example on the risk of death. So people, in this case, who got treated and died are 5, treated and alive are 95, control that are dead 10, and control that are alive is 90. Let me go back to, can you take this data because I go back to the formula? Can you write it down somewhere? Okay, so now if I go to the formula, let's calculate only the relative risk. So if I ask you to calculate the relative risk for this table, what will you write? A is 5. Okay, A plus B is 5 plus, what was it? 5 over 95, all divided by C is 10 over 100. How much is this? I think so. 0.5. And I mean, this is the for odds ratio is quite similar, but another number. Okay. Okay, this is the risk ratio for the risk of dying. If you were to calculate the opposite way, risk of surviving is not the inverse of 0.5. So it's not 1 over 0.5. You have to, if you apply the formula, you will see is the 1.056. Other formulas. This is a very important concept. The meta-analysis tool works with log scale. So after you or the software calculates the risk ratio, it will calculate the logarithmic, will do the pooled effect, and go back to the anti-log domain. This is because of this reason. So if you assume that one study reports that the risk is twice as high in group A, while another study reports that it is twice as high in group B. Assuming equal weights, these studies should balance each other with the combined effect showing equal risk, a risk ratio of 1. However, on the ratio scale, this corresponds to risk ratios of 0.5 and 2. So if you were to calculate inputting fake data so that you see that the number of dead people are twice as much as the number of survived, and vice versa, you get risk ratios that are 1 of 0.5 and 1 of 2. And if you take the mean, you see that is not a mean without effect, is 1.25, is not balanced. So if you instead work in the logarithmic domain, you will see that the logarithmic values of 0.5 and 2 should be these minus 0.693 and plus 0.693. That has a mean of 0 in the logarithmic domain. And if you go back take the opposite of the logarithmic, you have risk ratio of 1, which is balanced. So this is why the software has to use a logarithmic scale. Now, fixed effect model versus non-random effect model. This is the most standard one. This is used when you have homogeneous studies, means that they have very similar conditions and they all share a true common effect size. So they're all very close to the real value that they are trying to measure. And all the factors influencing this are similar. So in this case, what happens is that, of course, when you have a certain true value, you can see clearly in this graph, the true effect is the circle. For study 1, I mean, it's shared among the studies, but there will be observation error. So in the first study, okay, it's slightly underestimated. In the second study, it's slightly overestimated, and vice versa in the study number 3. So this is why you pulling the effects, you are closer to the real value. If the sample size was infinite, the sampling error would be 0. And well, this is the same concept, that just showing the distribution of error. It's very likely that, you know, for the law, I don't know the English, the law of the big numbers, la legge dei grandi numeri, when you have when n tends to infinity, you are close to the real value. This is just showing, I mentioned this when we saw the forest plot. So the weight in the fixed effect model is calculated as the inverse of the variance. So you can see this here. A singular weight is given by 1 over the variance of that study. The higher the variance, the lower the weight. So the higher the variance means the less precise the study, means I need to give less trust to this study. And then these are just to pull together all when you do the pooled effect. Random effect. Why is it important to have random effect? Because not every time the studies will be only affected by this sampling error. When there is, it may be that some studies are affected by different confounders, and so there may be some heterogeneity. For example, here it says the age. Maybe the age of the population under study is not exactly the same between my study and one's study, or wealth of participants, or many other. Maybe there is a bias towards, you know, more female than male, or vice versa. These are all things that can affect the results. So basically, the random effect model doesn't only take into account the variance due to the sampling error, but also the variance given by the fact that all the studies will not have the real value centered on. I don't know how to explain that. Let's read. To address this variation, we apply the random effect model, which is based on the hypothesis that the true effects are normally distributed around their mean. So it means that the true effect of each study is not any longer all aligned on the final value, as you were seeing in the previous slide. You see here all the circles are one on top of the other. In this case, it assumes that they are distributed in a certain way. And this is maybe more clear here. So we have two kinds of variations. The variation we were studying before in the fixed effect model was just this one. This is the true value, and this is the sampling error that was adding observed value. So there was a bit of error. But the fixed effect model wasn't taking into account that maybe this true value of the study is not exactly centered on the final value, but is normally distributed around this, like you were seeing here. So one study says here, one study says here, one study says here. So in this case, the observed value will be given by the true effect, which is this, plus Zi, which is this random effect model consideration of the variability, plus the older version of the fixed effect model of the sampling error. And this is more complex, but says the same. So study 1 will have this true effect size, but the observed one is here. The second study is slightly to the right, is not, right below the same circle, and the observed value is this square here, and so forth and so on. Okay, so these are estimation. So basically, this z number depends on the standard deviation of the distribution of the true effect. So how much they are spread around the final mean. This is called tau. And there is this formula which allows you to calculate this tau. You follow this. I mean, you follow. Software uses these equations to give you the number for tau. And then how do we assign the weight? In the same way, it's still the inverse of the variance, but in this case, the variance is not only this, which was 1 over the normal variance of the study, but plus this tau, which takes into account this random heterogeneity that can be there. So which one should we be using? If the studies are homogeneous or look homogeneous, then you should be using this. And in this case, the higher the number, the population of the study, the lower will be the variance, and then more weight will be given to these studies. In the random effect models, it's different, because with this kind of model, you also give power to smaller studies. So how do you select that? If the study are, qualitatively, you can look at the study and you can see whether they are very similar or not. But also the statistics comes towards you, because you can use, I think it's the next slide, you can use certain statistical variables like chi squared, q, I squared, all these values that allow you to understand whether your studies have high or low heterogeneity. And then based on that, you select what to do. If there is high level of heterogeneity, then you need to use random effect models. But when in doubt, you can just use random effect model, because if the between study variance is null, so if the studies are homogeneous enough, that part of the random model will tend to 0, and so basically you get the result of random or fixed effect model is the same. And these are just some of the variables that the software gives you: chi squared or I squared. So for example, I squared between 0 and 40 maybe is low heterogeneity, 30 to 60 moderate, 50 to 90 substantial, and 75, I don't know why this scale is not linear, but I think there are different ways of interpreting this. The lower the percentage, the lower the heterogeneity. Also, it gives you a p-value, so it tells you if this heterogeneity is significant, statistically significant or not. So if now we look at this forest plot again, despite its very low quality, you can see we are in the case where 2 studies are saying one effect, 2 sides are saying the other effect. This is in Italian below. It says in favor of this drug and in favor of the placebo. You can see that the final effect here is that it's in favor of the placebo, because the diamond is all on one side. And you can see here heterogeneity chi squared is 68.58, degree of freedom is 3, p-value is very low, and the heterogeneity I squared is 96%, is very high. But you can see it also from the graph. The more they are not aligned one on top of each other, the more heterogeneous the study are, because they are not saying the same thing, right? This is very detailed. I don't think you need to know that. And I think you all know what p-value means. This is another important thing. The tool will allow you to understand the publication bias. This is called funnel plot, and there are also indexes that you can calculate. Basically, it puts together a standard error of the study, which relate to study precision, and the study results. Normally, you would like to have this funnel plot. So ideally, if the overall effect is the one in the middle, you would like to have the studies more or less symmetrically distributed in the vertical symmetry, I mean, around this overall effect. If you only have studies here or only studies here, it means that there is publication bias. And how is it? This is an example. Okay, symmetrical or asymmetrical. Why is this possible? You might have seen already in your studies that if you complete, for example, the larger the study, the more one author will be, one researcher would be prone to publishing the results, even if they are negative, no? Because they have put a lot of effort in this huge randomized control trial, and then they see the point in publishing it. But if it's a small study that has low a negative result, let's say that this person is studying a new drug and they make a small study on 20 people and they see it's not working, then they don't really want to show that their new drug I mean, I shouldn't be saying that, but it's a problem because people tend to publish only positive results and not negative. So this is why you may have publication bias, basically. And one way to assess is this kind of funnel plot. Advantage, we have seen those. Limitations, okay, it's all statistical. It's quite likely that you will find heterogeneity among studies because of different reasons, and time. So the first thing, it could be that, but this is also true in systematic reviews, depending on your time frame, you may be including studies from 20 years ago. You have to understand what does it make sense to include at some point or exclude. Yes, this is, I think these slides were, I mean, I have a lot of maths content, but the important bit is that you understood more or less the process. Yeah. Do you have any question before I show an example? Okay, so if you have installed Meta Excel, it will appear somewhere on top of your Excel software. Yes. And these, I put 2 examples. I mean, you don't have this file, but you can, I will give it. I can't see that. Sorry. Okay, so il Meta Excel appears up here somewhere. This is, I put 2 examples. One is risk ratio for a discrete kind of variable example, and then we're going to see the mean difference for a continuous kind of example. Normally, okay, maybe, okay, what you do is this. You go on Meta Excel, input templates. Can you see also the pop-up? Yeah. Okay, so you have different types of input templates. What we are interested in right now, I think, is this one, binary number, because we're going to calculate the risk ratio. So you do copy. Now we'll just add it here. You see that the top is the same. Study, active. Okay. Now I will just focus on this side because it's already completed. So in this case, what we were studying, recidiva, it's Italian. It means, I don't know is this an English word? No, it means probability of something to reappear. For example, you have a hernia. Hernia, is that a word? Okay, you get a surgery. No, someone has an hernia, they get surgery, and then recidiva means how likely did it come back or not? Recounts, thank you. So I write it in English. Recounts. Okay. Reoccurrence. Okay. So in this case, we have active versus control. Well, in our case was this technique, surgical technique, Scholdice versus this other, which was Liechtenstein. These were all the studies that we had selected from our systematic literature review, and this was the total number of participants for example, Danielson had 89 participants that underwent Scholdice intervention, 9 of which had a reoccurrence. And then this is just calculated as the difference between the total number minus the people that got the reoccurrence. Then controls, there were 89 undergoing Liechtenstein, and 0 cases had this reoccurrence. And this is all the values extracted from the paper. Then what you do is you go down here, and by the way, all these the instructions, Meta Excel user guide is a PDF 50 pages long. If you have any doubt, you go and it gives you all the definition. But normally you just use 4 commands. One is MA input table. The first item here is the name of your variable. In this case is example recidiva, which is reoccurrence FE fixed effect. This is the kind of effect size that you want. In this case, relative risk. If you wanted, I don't know, the odds ratio, I think is like this. But all these are written in the Meta Excel user guide, so you can see all the different inputs. What does it mean? IV is inverse variance, so this is the standard way in which to calculate the weight. There are different ways, but in this case, the main one is inverse variance. And then you have to select the data where the software needs to calculate this without the study name, without the first line, basically, okay? And then it will create this. Then you have to look for rate ratio, low level of the confidence interval, high level of the confidence interval, I squared and Q. So this is just MA pooled effect. This will calculate the pool effect of and the argument is always this, okay? The argument is always the thing you calculated 1 minute ago. So MA pooled effect will give you this. Low confidence MA pooled effect LCI will give you the low value of the confidence interval. With H will give you the high value. I squared is called MA I squared, and Q is MA Cochrane Q. So these are the ones that you do. So these are the numbers here. Without before I show you the forest plot, what can you see from these numbers? First of all, let's look at I squared. We said the I squared is the heterogeneity. Is high or low? It's low, very low. So probably the fixed effect model is good enough, okay? And this is what we are applying at the moment. Then what do we see? Is if 1 is the change of effect, is the rhomboid figure that will be in the forest plot, is it gonna be crossing the 1 or not? No, because the low confidence interval is 1.4. Yes. If it had been 0.8, then yes, okay? Before I show you the forest plot, I just applied also the random effect model, which the only difference is this, instead of IV inverse variance, you have RE, random effect. And what you can see is that the numbers are very close. This is why, this is what I said before. When in doubt, use the random effect model, because if there is low heterogeneity, the results will be very close. Okay. Now, how do you see the plots? You click on results. In this case, we want to see fixed effect, and this is our forest plot. So you can see that most studies, apart from 2, are on the, well, Most studies are on the right side, but some are also on this other side here. This here you can see on the right how the weights were assigned. The element with the highest weight was 1, 2, 3, 4. 1, 2, 3, 4. This study, followed by this study, and so on and so forth. Yeah, and you can see from the I don't know if I can zoom. I cannot zoom from this shape here that we have a risk ratio that is on one side. Okay, dot plot, we haven't spoken about it, is similar to funnel plot concept, is used to understand publication bias, and this is the index I meant to say before and didn't remember the number. In this case, it says there is no asymmetry, but you can see also the funnel plot, which is what we were looking at before here. Table will give you a summary of all these numbers, and sensitivity is also a tool that can be useful. It basically shows you how all this data calculated until now would change if we were to, for example, exclude Danielson. So if I exclude Danielson, the pooled relative risk will be 2.79. Low confidence interval is 1.18. So you can see, for example, if you see that a study is a bit dodgy for whatever reason, like you do for the quality assessment in systematic reviews, that you see this study has very low quality, maybe I exclude. In the same way, you can see how is my final statistics going to change if I exclude this very bad quality study. Okay, the other example, very quickly, is on surgery duration. So this is a continuous variable in minutes. In this case, you need to have, not example, sorry. You need to have input, you have to have input template. We have continuous numbers. For example, weighted mean difference here, copy. You see is exactly the same as the one to the left. So I will go without the last one, which is not used. So in this case, we had that, again, Scholdice for Danielson had 89 patients. The mean duration of a surgery was 62 minutes, the standard deviation 27, while for the Liechtenstein was 60 minutes with standard deviation 26, and so on and so forth for all the other ones. If this is the same command, MA input table, I give the name of the variable. The method here cannot be, the effect size cannot be relative risk or odds ratio because it's continuous, so you need weighted mean difference, which is WMD in this case. Method for the fixed effect is again inverse variance, and the result here is that there is a weighted mean difference of 7. What does it mean? That on average, the pool effect is saying that the Scholdice technique lasted 7 minutes longer than the Liechtenstein. But there is very high heterogeneity, 85%. So maybe we need to calculate the random effect model. You can see the average is similar, but it will increase the variability. So the confidence interval is much more spread. So if I am to look for this result here, surgery random effect, you can see that yes, in general, one surgery is significantly longer than the other one by 7 minutes. This is the most probable value, but it could be, because it's a confidence interval, it could be 10 minutes, could be 2 minutes, yes? And then similar concept, you can look at the funnel plot, you can look at the dot plot and sensitivity. This is more or less it. Is there any question?